Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust-coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to something extraordinary? What if the very rocks beneath that orange sky hold secrets that could fundamentally change our understanding of life in the universe? In the summer of 2024, scientists analysing data from NASA's Perseverance rover made an announcement that sent ripples through the scientific community and beyond. They had discovered what might be the most compelling evidence yet that Mars once harboured life. Not the complex multicellular life on Earth today, but something far more ancient and mysterious. Microscopic organisms that may have thrived in the muddy sediments of an ancient Martian lake billions of years ago, when our solar system was still young and Mars was a very different world. This discovery didn't come from a dramatic moment of revelation, but from the patient, methodical work of a six-wheeled robot exploring a crater on the Martian surface. The Perseverance rover, which has been our eyes and hands on Mars since 2021, collected a sample from a rock formation with the poetic name of Bright Angel. Within that sample, scientists found something that made them pause and look closer. They found minerals that, on Earth, are almost always associated with the presence of life. But here's where our story becomes even more intriguing. These weren't just any minerals. They were vivianite and greigite, compounds that form through very specific chemical processes. On our planet, these minerals typically appear when organic matter, the building blocks of life, interacts with other chemicals in muddy environments. The reactions that create them are usually driven by microbes, tiny organisms that consume organic material and produce these minerals as byproducts of their metabolism. Finding them on Mars raises a profound question. Could similar processes have occurred on the red planet billions of years ago? The implications of this discovery extend far beyond the scientific community. If life once existed on Mars, even in its most primitive form, it would mean that life is not unique to Earth. It would suggest that given the right conditions, life might emerge naturally in our universe. This possibility has profound philosophical, scientific, and even spiritual implications for humanity. Are we alone in the cosmos, or are we part of a much larger tapestry of life that spans worlds and star systems? But let's step back for a moment and consider the journey that led us to this remarkable discovery. The story begins not with perseverance, but with decades of human curiosity about Mars. For generations, we have looked up at that red dot in our night sky and wondered what secrets it might hold. We've sent spacecraft to orbit it, land on it, and roam across its surface. Each mission has added pieces to an increasingly complex puzzle about Mars' past and its potential to support life. The location where Perseverance made this discovery is particularly significant. Jezero Crater in Mars' northern hemisphere wasn't chosen randomly. Scientists selected it precisely because they believed it once held water. Billions of years ago, when Mars had a thicker atmosphere and a warmer climate, Jezero Crater was home to an ancient lake. Rivers flowed into this lake, carrying sediments and potentially organic materials that settled on the lake bottom. Over vast stretches of time, these sediments were compressed and transformed into the rocks that Perseverance is now studying. The sample that has captured the attention of scientists worldwide came from a specific location within Jezero Crater called the Sapphire Canyon Sample Site. The name itself evokes a sense of beauty and mystery, fitting for a place that might hold evidence of ancient life. The rock formation here, known as Bright Angel, consists of fine-grained mudstones and coarser conglomerates. These are sedimentary rocks, formed from materials that were once suspended in water and then settled and hardened over millions of years. When Perseverance analysed this sample, using its sophisticated onboard instruments, it detected something unexpected: the presence of vivianite, an iron phosphate mineral that appears as dark blue or green crystals, and greigite, an iron sulfide mineral with a distinctive magnetic signature. On Earth, these minerals are like fingerprints of biological activity. They form when microbes interact with organic matter in oxygen-poor environments, exactly the kind of conditions that would have existed in the muddy depths of an ancient Martian lake. Dr. Joel Hurewitz, a planetary scientist at Stony Brook University who led the study, described the finding as a potential biosignature. This term might sound technical, but it represents something profound: evidence that life might have once existed in a place where we never expected to find it. The chemical reactions that appear to have created these minerals seem to have occurred shortly after the original mud was deposited on the ancient lake bottom, suggesting that if life was present, it was thriving in those early Martian environments. But science requires caution, especially when making claims as extraordinary as the possible discovery of life on another planet. While the presence of these minerals is exciting, researchers are careful to note that there are non-biological processes that could potentially create similar results. The challenge is that with current rover technology, it's impossible to completely rule out these alternative explanations. This uncertainty doesn't diminish the significance of the discovery, but it does highlight the careful, methodical nature of scientific investigation. What makes this discovery particularly compelling is the context in which it was found. Mars today is a harsh, seemingly lifeless world with a thin atmosphere, extreme temperature variations, and intense radiation from space. But billions of years ago, Mars was dramatically different. It had a thicker atmosphere that could trap heat and support liquid water on its surface. Rivers carved channels through its landscape, and lakes like the one in Jezero Crater provided stable environments where life might have taken hold. The transformation of Mars from a potentially habitable world to the barren planet today is one of the great mysteries of planetary science. Understanding this transformation could provide crucial insights not only into the history of Mars, but also into the factors that make planets suitable for life. If life did exist on ancient Mars, what happened to it? Did it disappear when the planet's climate changed? Or might it have found ways to survive in underground environments that we haven't yet explored? These questions bring us to one of the most fascinating aspects of astrobiology: the study of life in the universe. For decades, scientists have debated whether life is a rare cosmic accident that occurred only on Earth, or whether it's a natural consequence of chemistry and physics that might emerge wherever conditions are suitable. The possible discovery of ancient life on Mars would strongly support the latter view, suggesting that life might be far more common in the universe than we previously imagined. As we delve deeper into this story, we'll explore not just the scientific details of this remarkable discovery, but also its broader implications for our understanding of life, the universe, and our place within it. We'll journey through the history of Mars exploration, examine the sophisticated technology that made this discovery possible, and consider what it might mean for future missions to the Red Planet and beyond. The story of life on Mars is still being written, and we are privileged to witness its unfolding in real time. Whether you're here to learn about cutting-edge science, to ponder the profound questions raised by this discovery, or simply to let the wonder of space exploration carry you into peaceful sleep, this journey promises to be both enlightening and deeply satisfying. So settle in, relax, and let's explore together one of the most significant scientific discoveries of our time. Chapter 1. The Red Planet's Ancient Secret. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust-coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to life? It's a question that has driven countless missions to the Red Planet. We've sent rovers, orbiters, and landers all searching for clues about Mars's past. And recently, one mission, in particular, has yielded results that are sending ripples of excitement through the scientific community. A discovery so profound it could rewrite our understanding of life in the universe. The story begins with Perseverance, NASA's most advanced rover ever sent to Mars. Its mission: to seek signs of ancient life and collect samples for future return to Earth. Equipped with a suite of cutting-edge instruments, Perseverance has been meticulously exploring Jezero Crater, a location believed to have once been a lake billions of years ago. Think of it, a lake on Mars. Water, a key ingredient for life as we know it, existing freely on the surface of another planet. It's a tantalizing prospect, isn't it? and Jezero Crater offered the perfect environment to search for evidence of that ancient life. But it wasn't the overall mission objective that triggered this specific revelation. It was a single sample. A rock, carefully selected and extracted from the Martian surface. This sample, designated with a code, held a secret, one that scientists are only beginning to unravel. What made this sample so special? Well, it all started with the detection of unusual minerals. Minerals that, on Earth, are often associated with the presence of microbial life. Perseverance's instruments, particularly its Sherlock and pixel spectrometers, detected high concentrations of vivianite and greigite within the rock sample. Now, those names might not mean much to you right now, but trust me, they are significant. On Earth, vivianite, a hydrated iron phosphate mineral, often forms in sediments rich in organic matter. It's commonly found in environments where bacteria are actively breaking down organic material. Greigite, on the other hand, is an iron sulfide mineral that can be produced by certain types of bacteria. It's often found in anoxic or oxygen-poor environments, like those found in deep-sea sediments or within microbial mats. The presence of these minerals, together in a Martian rock sample, immediately raised eyebrows. It suggested that the environment in which this rock formed might have been conducive to microbial life. But was it just a coincidence? Could these minerals have formed through purely geological processes without the involvement of life? That's the question that scientists are now grappling with, and the answer could have profound implications for our understanding of life beyond Earth. Why does this discovery matter so much? Because it provides the strongest evidence yet that Mars may have once been habitable. It suggests that the conditions necessary for life to arise could have existed on our planetary neighbour. If life did exist on Mars, even in its simplest form, it would change everything. It would mean that life is not unique to Earth, that it can arise independently on other planets. It would revolutionize our understanding of biology, geology, and our place in the cosmos. Imagine the implications. If life can arise on 2 planets in the same solar system, what are the chances that it exists on countless other planets throughout the universe? This discovery is not just about Mars. It's about the search for life beyond Earth. It's about understanding the origins of life itself. It's about answering one of the most fundamental questions that humanity has ever asked: are we alone? This discovery, this single rock sample, has opened a new chapter in the story of Mars. But to truly appreciate the significance of this find, we need to understand the context in which it was made. We need to delve into the geological history of Jezero Crater, the ancient lake that holds the key to unlocking Mars's past. So, let's embark on a journey back in time, to a Mars that was very different from the cold, dry world today. A Mars with flowing rivers, stable lakes, and potentially life teeming in its waters. What secrets does Jezero Crater hold, and how did scientists know to look there in the first place? That's what we'll explore next as we journey into the heart of the red planet's ancient past. Jezero Crater. The name itself evokes images of a bygone era. A time when Mars was not the desolate, red wasteland we often picture, but a vibrant, potentially habitable world. But what exactly is Jezero Crater, and why did scientists pinpoint it as a prime location to search for signs of ancient life? The answer lies in its geological history. Jezero Crater is a large impact crater located in the Isidis Planitia region of Mars, just north of the equator. It spans approximately 49 kilometers or 30 miles in diameter, a vast basin carved into the Martian surface by a massive asteroid impact billions of years ago. But it's not just the crater itself that's interesting. It's what happened, the impact. Scientists believe that, billions of years ago, Jezero Crater was filled with water, forming a lake, an ancient Martian lake. How did they figure this out? Well, the evidence is written in the rocks. Orbital images of Jezero Crater reveal the presence of distinct geological features that are characteristic of ancient lake beds. For example, there are clear signs of ancient river systems that once fed into the crater. These river channels, now dry and eroded, can be seen winding their way across the Martian landscape, converging at the edge of the crater. Think of it like the Mississippi River flowing into the Gulf of Mexico. Except, instead of flowing into the Gulf, these ancient Martian rivers flowed into Jezero Crater, filling it with water over millions of years. These river systems carried sediments like sand and mud into the lake. Over time, these sediments accumulated on the lakebed, forming layers upon layers of sedimentary rock. And it's these sedimentary rocks that hold the key to understanding Jezero Crater's past. Sedimentary rocks are like time capsules, preserving information about the environment in which they formed. They can tell us about the composition of the water, the climate conditions, and even whether or not life existed in the lake. The presence of a delta, a fan-shaped deposit of sediment formed where a river enters a body of water, is another strong indication that Jezero Crater was once a lake. Deltas are common features on Earth, and they are often associated with rich ecosystems. The Nile Delta, for example, is a fertile region that has supported human civilization for thousands of years. The delta in Jezero Crater is not as lush as the Nile Delta, of course, but it's still a significant feature. It suggests that the lake was stable for a long period of time, allowing the river to deposit large amounts of sediment. So, how did scientists know to choose Jezero Crater as the landing site for Perseverance? It wasn't just a shot in the dark. It was the result of years of careful study and analysis of orbital data. Scientists used high-resolution images and spectroscopic data to map the geology of Jezero Crater in detail. They identified the ancient river channels, the delta, and the sedimentary rock layers. They also looked for evidence of minerals that are often associated with life, such as clays and carbonates. Based on this evidence, they concluded that Jezero Crater was one of the most promising locations on Mars to search for signs of ancient life. It was a place where water had once been abundant, where sediments had accumulated over time, and where the conditions might have been right for life to arise. The formation of sedimentary rocks is a crucial process in understanding the potential for life on Mars. These rocks are formed when layers of sediment, such as sand, silt, and clay, are deposited over time and then compressed and cemented together. Think of it like making a layered cake, but instead of frosting, you have layers of rock. These layers can trap and preserve organic molecules, the building blocks of life, and even fossilized remains of ancient organisms. On Earth, sedimentary rocks are a treasure trove of information about the history of life. And that's why scientists are so excited about the sedimentary rocks in Jezero Crater. They believe that these rocks could hold the key to unlocking the secrets of Mars's past and, potentially, to finding evidence of ancient life. The choice of Jezero Crater was a calculated risk, but it was a risk worth taking. It was a gamble that paid off, as Perseverance's recent discovery has shown. But the presence of vivianite and greigite, these intriguing minerals, doesn't automatically mean life existed on Mars. We need to understand how these minerals form and what their connection is to microbial life. That's where the chemistry comes in. But what exactly are biosignatures? And how can we use them to detect evidence of life on other planets? That's what we'll explore next, as we delve into the fascinating world of astrobiology and the search for life beyond Earth. The chemistry of life's fingerprints. What does that even mean? Well, in the search for life beyond Earth, scientists rely on something called biosignatures. These are essentially chemical or physical traces that indicate the presence of past or present life. Think of them as clues left behind by living organisms. Biosignatures can take many forms. They can be specific molecules, like DNA or proteins, that are unique to life. They can be isotopic ratios, which are variations in the relative abundance of different isotopes of an element. Or, as in the case of Perseverance's discovery, they can be certain minerals. We've already mentioned vivianite and greigite, but let's dive deeper into the science behind these minerals and why they are considered potential biosignatures. Vivianite, as you may recall, is a hydrated iron phosphate mineral. On Earth, it often forms in sediments rich in organic matter, such as lake beds, swamps, and bogs. It's typically found in anoxic environments where oxygen is scarce. The formation of vivianite is often linked to the activity of bacteria. When organic matter decomposes, it releases phosphate, which can then react with iron in the sediment to form vivianite. The presence of vivianite, therefore, can suggest that organic matter was once present in the environment and that bacteria were actively involved in its decomposition. Now, let's talk about greigite. Greigite is an iron sulfide mineral that is also associated with microbial activity. It's often found in anoxic environments, like those found in deep-sea sediments or within microbial mats. Some types of bacteria can actually produce greigite as a byproduct of their metabolism. These bacteria use iron and sulfur to generate energy, and greigite is one of the waste products of this process. So, Finding vivianite and greigite together in a rock sample is particularly intriguing. It suggests that the environment in which the rock formed was not only rich in organic matter, but also conducive to the growth of certain types of bacteria. But here's the catch. These minerals can also form through purely geological processes without the involvement of life. For example, vivianite can form when phosphate-rich fluids react with iron-bearing rocks. Greigite can form when iron and sulfur react in the presence of water. So, how can scientists tell whether the vivianite and greigite found on Mars are truly biosignatures or just the result of non-biological processes? That's where the detailed analysis comes in. Scientists need to look at the specific characteristics of the minerals, such as their crystal structure, their chemical composition, and their isotopic ratios. They also need to consider the geological context in which the minerals were found. For example, if the vivianite and greigite are found in close association with other organic molecules, or if they have unusual isotopic ratios, that would strengthen the case that they are biosignatures. The chemical processes that create these minerals are complex, but they are essential to understanding the potential for life on Mars. By studying these processes, scientists can learn more about the conditions that existed on Mars billions of years ago and whether those conditions were conducive to life. The connection between these minerals and microbial life on Earth is well established. But it's important to remember that Earth is not Mars. The geological history and environmental conditions on Mars are very different from those on Earth. So, even if vivianite and greigite are strong indicators of life on Earth, we can't automatically assume that they have the same meaning on Mars. That's why it's so important to gather as much evidence as possible and to carefully consider all the possible explanations for the presence of these minerals. The scientific process demands rigor and skepticism. The significance of finding these minerals on Mars lies in the fact that they are potential biosignatures. They suggest that the environment in which the rock formed might have been habitable and that life might have once existed there. But it's just one piece of the puzzle. To truly understand the significance of this discovery, we need to delve into the details of Perseverance's mission. How did the rover find these minerals? What instruments did it use to analyze the rock sample? And what steps did it take to ensure that the results were accurate? So, let's rewind the clock and follow Perseverance on its journey of discovery. From its dramatic landing on the Martian surface to the moment it uncovered the secrets hidden within that single rock sample. How did Perseverance make this groundbreaking discovery? What were the key moments in its journey that led to this point? That's what we'll explore next as we delve into the rover's mission and the sophisticated instruments it used to analyze Martian rocks. Chapter 2. Jezero Crater. Window to Mars's past. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust-coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to a thriving lake, teeming with the potential for life? The story we've begun, the one sparked by Perseverance's incredible discovery, takes us back in time, to a period when Mars was a vastly different place. To understand the significance of those unusual minerals, we need to understand the environment in which they formed. We need to travel to Jezero Crater. Think of Jezero Crater as a giant, open history book etched onto the Martian surface. It's a geological marvel, a place where the secrets of Mars's past are laid bare for us to read. But how did this crater form? And why did scientists pinpoint it as the perfect place to search for signs of ancient life? The answer lies in a cataclysmic event that occurred billions of years ago. A massive asteroid hurtling through space slammed into the Martian surface with unimaginable force. The impact carved out a vast depression, a gaping wound in the planet's crust. This, my friends, was the birth of Jezero Crater. Now, craters are common throughout the solar system. What makes Jezero so special? Well, the key is water. Scientists believe that in its early history, Mars was far warmer and wetter than it is today. Rain fell from the sky, rivers flowed across the landscape, and lakes dotted the surface. And Jezero Crater, with its low-lying position, became a natural basin, a gathering place for all that water. Imagine, if you will, a vast lake filling the crater, its waters lapping against the rim. Rivers, fed by melting glaciers and rainfall, snaked their way across the Martian plains, eventually emptying into Jezero. These weren't just trickles of water, these were substantial rivers, carving deep channels into the landscape. You can actually see the evidence of these ancient river systems today. From orbit, they appear as winding, fan-shaped deposits, like the deltas of rivers on Earth. These deltas are composed of sediment, sand, silt, and clay that was carried by the rivers and deposited at the mouth of the lake. It's like a geological time capsule, preserving a record of the materials that were flowing into Jezero billions of years ago. But how did scientists know that Jezero Crater was once a lake? It wasn't just a lucky guess. Years of painstaking research, using data from orbiting satellites and sophisticated computer models, led them to this conclusion. They analysed the topography of the crater, the composition of the rocks, and the patterns of the sedimentary deposits. The evidence was compelling. The presence of clay minerals, which form in the presence of water, was a strong indicator. The shape and structure of the deltas further supported the idea of an ancient lake, and the overall geological context of the region painted a picture of a warmer, wetter Mars. So, Jezero Crater was once a lake. That much we know. But why was this particular location chosen for exploration? Why not any other crater or basin on Mars? The answer, as you might suspect, lies in the potential for finding evidence of past life. Lakes are ideal environments for life to flourish. They provide a stable source of water, a variety of nutrients, and a protective environment from the harsh radiation of space. On Earth, lakes are teeming with microbial life from the surface to the deepest depths. It's reasonable to assume that if life ever existed on Mars, it might have thrived in a similar environment. And that's where the sedimentary rocks come in. Sedimentary rocks are formed from the accumulation of sediments over time. As layers of sand, silt, and clay are deposited, they are gradually compressed and cemented together, forming solid rock. These rocks can trap and preserve organic molecules, the building blocks of life, and even fossilized remains of microorganisms. Think of sedimentary rocks as the pages of a history book, each layer telling a story about the past. By studying these rocks, scientists can reconstruct the ancient environment of Jezero Crater and search for clues about whether life ever existed there. The layers of sediment can reveal changes in the lake's environment over time. They can show periods of increased rainfall, changes in water chemistry, and even evidence of volcanic activity. It's like reading the rings of a tree, but on a much grander scale. And the best part? Jezero Crater offers a diverse range of sedimentary rocks, each with its own unique story to tell. There are fine-grained mudstones, coarse-grained sandstones, and even rocks that appear to have been formed from the precipitation of minerals from the lake water. This variety provides scientists with multiple opportunities to find evidence of past life. But let's be clear, finding evidence of past life on Mars is an incredibly challenging task. It's not like stumbling upon a dinosaur bone. Any evidence of Martian life is likely to be microscopic, subtle, and potentially ambiguous. That's why scientists need to be so careful in their analysis and interpretation of the data. And that's why Perseverance is equipped with such sophisticated instruments. It's not just a rover, it's a mobile laboratory capable of analyzing rocks and soils with incredible precision. It can measure the chemical composition of rocks, identify different minerals, and even search for organic molecules. But even with all this technology, the search for life on Mars is still a long shot. There's no guarantee that Perseverance will find anything definitive, but the potential reward, the discovery that we're not alone in the universe, is worth the effort. So, as Perseverance continues its exploration of Jezero Crater, remember the ancient history of this remarkable place. Remember the asteroid impact, the flowing rivers, and the vast lake that once filled the crater. Remember the sedimentary rocks, the potential time capsules that may hold the key to unlocking the secrets of Martian life. And remember that you are witnessing a pivotal moment in human history. We are on the cusp of potentially answering one of the most fundamental questions of all: are we alone? But to truly understand the significance of Perseverance's findings, we need to delve deeper into the science behind biosignatures. What exactly are they, and how can we be sure that they are truly indicative of life? Because in the next chapter, we'll be exploring the chemistry of life's fingerprints, focusing on those intriguing vivianite and greigite minerals and understanding why their presence on Mars is so incredibly significant. Chapter 3. The chemistry of life's fingerprints. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust, coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to life? The discovery of unusual minerals within a sample collected by the Perseverance rover has sent ripples of excitement and cautious optimism throughout the scientific community. But what exactly are these minerals, and why are they so significant? The answer lies in understanding the chemistry of life's fingerprints. On Earth, life leaves behind telltale signs, chemical clues that indicate biological activity. These clues, known as biosignatures, can take many forms, from complex organic molecules to the unique isotopic ratios of certain elements. But perhaps the most visually striking and easily recognizable biosignatures are certain minerals that form under specific conditions often associated with microbial life. Two minerals in particular, vivianite and greigite, have captured the attention of scientists studying the Martian sample. These minerals, while not definitive proof of past life, are certainly intriguing indicators that warrant further investigation. Think of them as breadcrumbs hinting at a potential feast of discovery. So, what makes these minerals so special? Let's start with vivianite. Vivianite is a hydrated iron phosphate mineral, typically found in association with organic matter in sediments and soils. Its formation is often linked to the presence of iron-reducing bacteria, microorganisms that thrive in oxygen-poor environments. Imagine a murky pond on early Earth teeming with microscopic life. As these organisms die and decompose, they release iron into the surrounding water. Under the right conditions, this iron can react with phosphate ions, also released from decaying organic matter, to form vivianite crystals. These crystals often appear as beautiful, radiating clusters of blue or green needles, a testament to the hidden world of microbial activity. But how could this be possible on Mars? If vivianite were found in the Martian rock, it would suggest that similar conditions once existed on the red planet, a time when liquid water was abundant and microbial life may have flourished. The presence of vivianite would be a strong indicator that the environment was once conducive to life, a crucial piece of the puzzle in our search for extraterrestrial life. Now, let's turn our attention to greigite. Greigite is an iron sulfide mineral known for its magnetic properties and its association with anaerobic environments. Like vivianite, greigite is often formed by the activity of microorganisms, particularly sulfate-reducing bacteria. Picture a dark, oxygen-deprived sediment layer where sulfate-reducing bacteria are hard at work, breaking down organic matter and producing hydrogen sulfide as a byproduct. This hydrogen sulfide then reacts with iron ions in the surrounding environment to form greigite. Greigite crystals are typically black or dark brown in color and often occur as tiny, rhomboidal clusters resembling miniature raspberries. On Earth, greigite is found in a variety of environments, including salt marshes, hydrothermal vents, and even the guts of certain animals. Its presence is often indicative of active microbial metabolism and the presence of anaerobic conditions. If greigite were found on Mars, it would suggest that similar processes may have occurred in the past, a time when anaerobic microorganisms could have thrived in the Martian subsurface. The discovery of greigite would be another tantalizing clue in our search for past life on Mars, a sign that the red planet may have once been a more hospitable place. But the significance of vivianite and greigite extends beyond their association with microbial life. These minerals can also act as preservatives, trapping and protecting organic molecules from degradation. Imagine a tiny pocket of vivianite or greigite encapsulating ancient organic compounds, like a time capsule preserving the chemical remnants of past life. These preserved organic molecules could provide invaluable insights into the types of organisms that may have once lived on Mars, their metabolic processes, and their evolutionary history. They could even reveal the building blocks of life itself, the fundamental molecules that are essential for all known forms of life. The discovery of vivianite and greigite on Mars would not only suggest that life may have once existed on the red planet, but it could also provide us with a window into the past, a glimpse into the ancient ecosystems that may have thrived billions of years ago. It would be like finding a fossilized fingerprint, a lasting reminder of a world that once was. The chemical processes that create these minerals are fascinating in their own right. They involve complex interactions between water, minerals, and microorganisms, all working together in a delicate balance. Understanding these processes is crucial for interpreting the geological record and for identifying potential biosignatures on other planets. For example, the formation of vivianite requires the presence of iron, phosphate, and organic matter, as well as reducing conditions. These conditions are often found in environments where microorganisms are actively breaking down organic matter and releasing iron and phosphate into the surrounding water. Similarly, the formation of greigite requires the presence of iron, sulfur, and anaerobic conditions. These conditions are often found in environments where sulfate-reducing bacteria are thriving, producing hydrogen sulfide that reacts with iron to form greigite. By studying these chemical processes in detail, scientists can develop a better understanding of the conditions that are necessary for the formation of these minerals and for the preservation of organic matter. This knowledge can then be applied to the search for life on other planets, helping us to identify potential biosignatures and to interpret the geological record. But it's important to remember that the discovery of vivianite and greigite on Mars is not a slam dunk. These minerals can also form through non-biological processes, so it's crucial to consider all possible explanations before jumping to conclusions. For example, vivianite can form through the weathering of iron-rich rocks in the presence of phosphate-rich fluids. Similarly, greigite can form through the alteration of other iron sulfide minerals under certain conditions. Therefore, it's essential to carefully analyze the context in which these minerals are found, looking for other clues that might support a biological origin. Are there other biosignatures present, such as organic molecules or isotopic anomalies? Is the mineralogy of the surrounding rocks consistent with a biological origin? By carefully considering all of the available evidence, scientists can build a strong case for or against the presence of past life on Mars. It's a complex and challenging process, but the potential reward is immense. Imagine the moment of discovery, the realization that we may have finally found evidence of life beyond Earth. It would be a monumental achievement, a turning point in human history. It would change the way we think about our place in the universe and our understanding of the origins of life. But even if we don't find definitive proof of past life on Mars, the search itself is a valuable endeavor. It pushes the boundaries of our knowledge, inspires innovation, and fosters a deeper appreciation for the wonders of the natural world. The quest to understand the chemistry of life's fingerprints is a journey that will continue for many years to come. It's a journey that will take us to the far reaches of our solar system and beyond, in search of answers to some of the most fundamental questions about life in the universe. And the Perseverance rover, with its sophisticated suite of instruments, is playing a crucial role in this quest. It's our robotic explorer, our eyes and ears on Mars, tirelessly collecting data and sending it back to Earth for analysis. But how exactly did Perseverance make this groundbreaking discovery? What instruments did it use to analyze the Martian rocks, and how did it ensure the accuracy of its results? The answer to that question lies in the next chapter, where we'll delve into Perseverance's incredible journey of discovery. Chapter 4: Perseverance's Journey of Discovery. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust, coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to something more? The story of Perseverance's journey is one of meticulous planning, cutting-edge technology, and relentless scientific curiosity. It's a story that began long before the rover even touched down on Martian soil. Years of research and analysis went into selecting Jezero Crater as the ideal landing site, a place believed to hold the keys to unlocking Mars's ancient past. But how did scientists choose this specific location, and what were they hoping to find? The selection of Jezero Crater wasn't a random decision. It was based on extensive satellite imagery and geological data that revealed compelling evidence of a past lake environment. Scientists had identified ancient river channels that once flowed into the crater, creating a delta where sediment and organic material could have accumulated over billions of years. This delta became a prime target in the search for potential biosignatures, those elusive fingerprints of past life. Before Perseverance could even begin its mission, it had to survive the harrowing descent to the Martian surface. The entry, descent, and landing, often referred to as EDL, is a nail-biting sequence of events that has earned the nickname 7 Minutes of Terror. Imagine the intense heat of atmospheric entry, the deployment of a massive parachute, and the final, delicate touchdown orchestrated by a rocket-powered sky crane. It's a breathtaking feat of engineering that had to work perfectly for the mission to succeed. And it did. With Perseverance safely on the ground, the real work began. The rover is equipped with a suite of sophisticated instruments designed to analyze the Martian rocks and soil in unprecedented detail. These tools include cameras that can capture high-resolution images, spectrometers that can identify the chemical composition of materials, and a laser that can vaporize rock samples for analysis. But how do these instruments actually work, and what kind of information can they reveal? One of the most important instruments on Perseverance is the SuperCam, a remote sensing device that can analyze the chemical composition of rocks from a distance. It uses a laser to zap rocks, creating a small plasma that can then be analyzed by spectrometers. This allows scientists to identify the elements and minerals present in the rock without having to physically touch it. Think of it as a high-tech magnifying glass that can see the invisible. Another crucial instrument is the ShearLock, or Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. ShearLock uses a laser and spectrometers to detect organic molecules and minerals that may be associated with past life. It's like a detective searching for clues, looking for the telltale signs of biological activity. But what exactly are organic molecules, and why are they so important in the search for life? Organic molecules are the building blocks of life as we know it. They are complex molecules that contain carbon and other elements such as hydrogen, oxygen, and nitrogen. While organic molecules can be formed through non-biological processes, their presence in certain geological contexts can be a strong indicator of past life. ShearLock is designed to identify these molecules and help scientists determine whether they are of biological origin. Perseverance also carries a drill that can collect rock core samples for later retrieval. These samples are carefully sealed in airtight tubes and stored on board the rover, awaiting a future mission that will bring them back to Earth for further analysis. This sample return mission is a critical part of the overall Mars exploration program, as it will allow scientists to study the Martian rocks in the best-equipped laboratories on Earth. But why is it so important to bring the samples back to Earth rather than analyzing them on Mars? While Perseverance's instruments are incredibly advanced, they are limited by their size and power constraints. Earth-based laboratories have access to much more sophisticated equipment and techniques, allowing scientists to conduct a wider range of analyses with greater precision. By bringing the Martian samples back to Earth, scientists can unlock even more secrets about Mars's past and its potential for life. The process of collecting and storing the samples is a meticulous one. Perseverance first uses its drill to extract a core sample from the rock. The sample is then carefully measured and photographed before being sealed in a titanium tube. The tube is then stored in a special compartment on the rover, ready for eventual retrieval. This process is repeated for each sample, ensuring that they are preserved in pristine condition for future study. But it wasn't just about drilling and collecting. Perseverance needed to navigate the treacherous terrain of Jezero Crater, traversing rocky landscapes, sandy dunes, and steep slopes. The rover is equipped with a sophisticated navigation system that allows it to autonomously navigate these obstacles, using its cameras and sensors to create a 3D map of its surroundings. It's like giving the rover a brain and a set of eyes, allowing it to explore Mars with minimal human intervention. The rover's wheels are specially designed to provide traction on the Martian surface, allowing it to climb over rocks and navigate sandy terrain. The wheels are also equipped with sensors that monitor the rover's movement and stability, ensuring that it doesn't get stuck or tip over. It's a testament to the ingenuity of engineers who have designed a vehicle that can withstand the harsh conditions of Mars. As Perseverance explored Jezero Crater, it sent back a constant stream of data and images to Earth. Scientists around the world eagerly analyzed this information, searching for clues about Mars's past and its potential for life. The data revealed a complex and dynamic landscape with evidence of ancient river systems, lakes, and hydrothermal activity. But what exactly is hydrothermal activity, and why is it important in the search for life? Hydrothermal activity occurs when water is heated by volcanic activity or geothermal energy. This hot water can dissolve minerals from the surrounding rocks, creating chemical-rich fluids that can support microbial life. On Earth, hydrothermal vents are found in the deep ocean, where they provide a haven for unique ecosystems that thrive in the absence of sunlight. The discovery of hydrothermal activity on Mars would be a significant step forward in the search for life beyond Earth. One of the most exciting discoveries made by Perseverance was the identification of organic molecules in several rock samples. These molecules were found in areas that were once part of an ancient lakebed, suggesting that they may have formed in a habitable environment. While the presence of organic molecules doesn't necessarily prove that life existed on Mars, it does provide tantalizing evidence that the planet may have once been capable of supporting life. The detection of these organic molecules was a major breakthrough in the search for life on Mars. It provided strong evidence that Jezero Crater was once a habitable environment with the potential to support microbial life. But the question remained, were these organic molecules of biological origin, or were they formed through non-biological processes? This is where the analysis of specific minerals becomes so crucial. The moment of discovery, the moment that changed everything, came when Perseverance analysed a particular rock sample. The data revealed the presence of vivianite and greigite, minerals often associated with microbial activity on Earth. These minerals are known to form in environments where organic matter is decaying, suggesting that they may have been formed by ancient Martian microbes. But how do these minerals form, and what is their connection to microbial life? Vivianite is a hydrated iron phosphate mineral that is often found in association with decaying organic matter. It forms when iron reacts with phosphate in the presence of water and organic material. On Earth, vivianite is commonly found in sediments and soils where microbial activity is high. Its presence on Mars suggests that similar processes may have occurred in Jezero Crater billions of years ago. Greigite is an iron sulfide mineral that is also associated with microbial activity. It forms in anaerobic environments where bacteria use sulfur to break down organic matter. On Earth, greigite is often found in sediments and soils that are rich in organic material and low in oxygen. Its presence on Mars further supports the idea that Jezero Crater was once a habitable environment for microbial life. The discovery of vivianite and greigite in a Martian rock sample was a watershed moment in the search for life beyond Earth. It provided compelling evidence that Mars may have once been home to microbial life, and that these microbes may have played a role in the formation of these minerals. But the scientific process demands caution, and scientists are careful to consider all possible explanations for the presence of these minerals. The discovery of these minerals sparked intense debate and further investigation. Scientists are now working to determine whether these minerals could have formed through non-biological processes such as volcanic activity or chemical reactions. They are also conducting experiments to simulate the conditions on ancient Mars to see if they can replicate the formation of vivianite and greigite in the absence of life. Perseverance's journey of discovery has been a remarkable feat of engineering and scientific exploration. From its daring landing on the Martian surface to its meticulous analysis of Martian rocks, the rover has provided us with unprecedented insights into the history of Mars and its potential for life. But this is just the beginning of the story. The samples collected by Perseverance will eventually be returned to Earth, where they will be subjected to even more rigorous analysis. But this discovery was only the beginning, because next, we uncover the secrets hidden within the chemistry of these minerals and how they serve as potential fingerprints of life itself. Chapter 5. When Mars Was Alive, Reconstructing Ancient Worlds. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust-coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to something far more extraordinary? We've journeyed together through the initial discovery, the intriguing minerals, and the meticulous work of the Perseverance rover. Now, we stand on the precipice of a breathtaking possibility, a Mars teeming with life. It's a picture that challenges everything we thought we knew about the red planet. But how can we even begin to imagine such a transformation? How do we rewind the clock billions of years and see Mars not as it is, but as it once was? Let's start with the obvious: water. Today, Mars is a desert. But the evidence is overwhelming that it wasn't always this way. Jezero Crater, our focal point, was once a lake. A large, stable lake fed by a network of rivers. Imagine the scene: water cascading down from the crater walls, carving channels and depositing sediment. Think of the Mississippi River on Earth, but on Mars. These Martian rivers flowed for perhaps millions of years, carrying with them minerals, organic molecules, and potentially the very building blocks of life. The presence of water is just the beginning. To paint a truly vivid picture, we need to consider the atmosphere. Early Mars likely had a much thicker atmosphere than it does today, an atmosphere rich in carbon dioxide and other greenhouse gases. This thicker atmosphere would have trapped more heat from the sun, creating a warmer, more hospitable climate. Imagine a world where liquid water could exist on the surface without immediately freezing or boiling away. A world where temperatures were mild enough for complex chemical reactions to occur, the kind of reactions that are essential for life as we know it. But how warm are we talking? Scientists believe that the average temperature on early Mars may have been above freezing, perhaps even in the range of 10 to 20 degrees Celsius, or 50 to 68 degrees Fahrenheit. That's comparable to a pleasant spring day on Earth. Now, picture this. You're standing on the shore of Jezero Lake, the sun warming your face, a gentle breeze rustling through the Martian vegetation. Yes, vegetation. While we haven't found direct evidence of macroscopic plant life, the presence of microbial life could have supported simple ecosystems. Perhaps the lake was fringed with microbial mats, similar to the stromatolites found in ancient rocks on Earth. These mats would have been teeming with microorganisms, photosynthesizing, consuming organic matter, and creating a vibrant, albeit microscopic, ecosystem. The water itself would have been rich in minerals, providing the essential nutrients for life. Imagine the interplay of sunlight, water, and minerals, creating a chemical soup that was ripe for the emergence of life. But what about the color? We know Mars is red today, but what color would it have been billions of years ago? The presence of water and vegetation would have undoubtedly altered the landscape. The lake itself would have been a shimmering blue, reflecting the orange sky. The surrounding terrain may have been dotted with patches of green, brown, and yellow, depending on the type of microbial life present. The rivers that fed Jezero Lake would have been ribbons of turquoise cutting through the Martian landscape. The crater walls, sculpted by erosion, would have been a mosaic of colours, revealing the different layers of rock and sediment. But let's not get carried away with idyllic imagery. Early Mars was likely a dynamic and sometimes volatile environment. Volcanic eruptions would have spewed ash and gases into the atmosphere, temporarily darkening the sky and altering the climate. Impact events, though less frequent than in the early solar system, would have still occurred, creating shockwaves and depositing debris across the landscape. These events would have been disruptive, but they also could have provided new opportunities for life to evolve and adapt. Imagine the resilience of these early Martian lifeforms, surviving volcanic eruptions, asteroid impacts, and fluctuations in climate. Their ability to adapt and thrive in such challenging conditions would have been a testament to the power of life itself. Now, let's talk about the big question: what happened to this potentially habitable world? Why did Mars transform from a warm, wet planet to the cold, dry desert today? The answer lies in the loss of its atmosphere. Over billions of years, Mars gradually lost its atmosphere to space. There are several reasons for this. First, Mars is smaller than Earth and therefore has weaker gravity. This made it easier for atmospheric gases to escape into space. Second, Mars lost its global magnetic field early in its history. On Earth, our magnetic field acts as a shield, deflecting charged particles from the Sun. Without a magnetic field, the solar wind, a stream of charged particles emanating from the Sun, can directly interact with the atmosphere, stripping away its gases. As Mars lost its atmosphere, the planet cooled down. The water on the surface began to freeze, eventually forming the ice caps today. The remaining water likely exists as subsurface ice, hidden beneath the Martian soil. The loss of water and atmosphere had a profound impact on the planet's habitability. The conditions that once supported life became increasingly harsh, eventually leading to the extinction of any surface-dwelling organisms. But what about the possibility of life surviving underground? Could there be microbial ecosystems still thriving in the Martian subsurface, shielded from the harsh radiation and extreme temperatures of the surface? This is a question that scientists are actively investigating. Imagine a hidden world beneath the Martian surface, a network of underground aquifers and caves teeming with microbial life. These organisms could be deriving energy from chemical reactions, utilizing the minerals and water available in the subsurface. These hypothetical Martian microbes could be similar to extremophiles found on Earth, organisms that thrive in extreme environments such as hot springs, deep-sea vents, and acidic lakes. These Earth-based extremophiles provide a glimpse into the types of organisms that could potentially survive on Mars. The search for subsurface life on Mars is a challenging but potentially rewarding endeavor. It would require drilling deep into the Martian crust, collecting samples, and analyzing them for signs of life. This is a technologically demanding task, but it is one that is within our reach. But for now, let's return to our reconstruction of ancient Mars. We've painted a picture of a world with flowing rivers, stable lakes, and a potentially habitable environment. But how can we be sure that this picture is accurate? The answer lies in the rocks. The sedimentary rocks of Jezero Crater hold clues to the past, providing a record of the environmental conditions that existed billions of years ago. By studying these rocks, we can piece together the history of Mars and gain a better understanding of its potential for life. Imagine holding a piece of Martian rock in your hand, a rock that has witnessed billions of years of history. Within that rock are tiny grains of sediment, each one a time capsule containing information about the ancient Martian environment. By analyzing the composition of these grains, we can determine the types of minerals that were present, the temperature and salinity of the water, and the presence of any organic molecules. This information can help us to reconstruct the ancient Martian climate and determine whether the environment was suitable for life. The discovery of vivianite and greigite, the minerals we discussed earlier, is a significant piece of the puzzle. These minerals are often associated with microbial activity on Earth, suggesting that similar processes may have occurred on Mars. But it's important to remember that correlation does not equal causation. The presence of these minerals does not necessarily prove that life existed on Mars. There could be other, non-biological explanations for their formation. That's why scientists are so careful and meticulous in their analysis. They consider all possible explanations, conduct rigorous experiments, and subject their findings to peer review. It's a slow and painstaking process, but it's the only way to ensure that our conclusions are accurate and reliable. The reconstruction of ancient Mars is an ongoing process. As we gather more data from Perseverance and other missions, our understanding of the red planet's past will continue to evolve. Imagine a future where we have a complete and detailed picture of ancient Mars, a picture that reveals the secrets of its past and sheds light on the potential for life beyond Earth. But what if we actually find definitive evidence of past life on Mars? What would that mean for our understanding of the universe and our place within it? That's a question we'll explore in the next chapter. We'll delve into the search for life beyond Earth, the science of astrobiology, and the profound implications of discovering that we are not alone in the cosmos. The discovery of potentially habitable conditions on ancient Mars is a major step forward in our quest to understand life's origins and its potential distribution throughout the universe. But this discovery was only the beginning, because next we uncover the science behind the search for life beyond Earth and the profound implications it holds for humanity. Chapter 6: The Search for Life. Beyond Earth. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust-colored soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbor, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to something more? We've journeyed together through the red planet's ancient history, exploring the intriguing evidence unearthed by the Perseverance rover. We've peered into the depths of Jezero Crater, a place that once held a vast lake fed by rushing rivers. And we've examined the peculiar chemistry of Martian rocks, discovering minerals that, on Earth, are intimately linked to life itself. The presence of vivianite and greigite, those subtle fingerprints of biological activity, has ignited a spark of hope. But what does it all mean? These tantalizing clues from Mars have opened up a much larger question. Are we alone in the universe? The search for life beyond Earth, or astrobiology, is no longer the realm of science fiction. It's a rapidly growing field of scientific inquiry, fueled by incredible technological advancements and a deeper understanding of the conditions that make life possible. For centuries, humans have looked up at the stars and wondered if there were others out there. Now, we are closer than ever to answering that age-old question. But how do we even begin to look for life on other planets? It's not as simple as pointing a telescope and hoping to see waving aliens. The search is far more nuanced, requiring a multidisciplinary approach that draws on the expertise of biologists, geologists, chemists, and astronomers. One of the most fundamental approaches is to look for what we call biosignatures. These are indicators that life, past or present, may be present on a planet. As we've seen with the Martian samples, biosignatures can be chemical compounds, mineral formations, or even specific patterns in the geological record. They are essentially clues left behind by living organisms. Think of it like a detective investigating a crime scene. The detective doesn't necessarily witness the crime, but they look for fingerprints, footprints, or other pieces of evidence that can point to the perpetrator. Similarly, astrobiologists search for biosignatures that could indicate the presence of life, even if that life is long gone. But identifying a true biosignature is a complex challenge. Many non-biological processes can mimic the signs of life. For example, certain geological formations can resemble microbial structures, and some chemical compounds can be created through purely inorganic reactions. This is why scientists must be incredibly cautious and rigorous in their analysis. They need to rule out all other possible explanations before concluding that particular finding is truly indicative of life. That's where the study of extremophiles comes in. These are organisms that thrive in extreme environments on Earth, places that were once thought to be uninhabitable. You can find them in boiling hot springs, deep sea vents, and even in highly acidic or alkaline environments. Extremophiles have taught us that life is incredibly adaptable and can exist in conditions that we never thought possible. And that understanding has profound implications for the search for life beyond Earth. If life can thrive in such extreme environments on our own planet, then it could potentially exist in similar environments on other planets or moons. For example, consider Europa, one of Jupiter's moons. Europa is covered in a thick layer of ice, but scientists believe that beneath that ice lies a vast ocean of liquid water. The heat from Jupiter's tidal forces could be enough to keep that ocean liquid, and hydrothermal vents on the ocean floor could provide the energy needed to support life. Similarly, Enceladus, one of Saturn's moons, has geysers that spew water vapor and ice particles into space. Scientists have analyzed these plumes and found evidence of organic molecules, the building blocks of life. This suggests that Enceladus may also harbor a subsurface ocean with the potential for life. These are just two examples of the many potentially habitable environments that exist in our solar system. And beyond our solar system, the possibilities are even more staggering. The discovery of exoplanets, planets orbiting other stars, has revolutionized our understanding of planetary systems. We now know that planets are incredibly common in the universe, and that many of these exoplanets are potentially habitable. Some are rocky planets, similar in size and composition to Earth, orbiting within the habitable zone of their stars, where liquid water could exist on the surface. Imagine the sheer number of stars in our galaxy, the Milky Way, and then imagine the number of galaxies in the observable universe. The number of potentially habitable planets is almost unfathomable. It's hard to believe that Earth is the only place where life has arisen, but finding life on these distant exoplanets is an enormous challenge. They are incredibly far away, and even with our most powerful telescopes, it's difficult to gather detailed information about their atmospheres and surfaces. One promising technique is to analyze the light that passes through an exoplanet's atmosphere. By studying the wavelengths of light that are absorbed or scattered by the atmosphere, scientists can determine its composition. The presence of certain gases, such as oxygen or methane, could be a sign of biological activity. However, like with biosignatures on Mars, scientists must be very careful in interpreting these atmospheric signals. There are many non-biological processes that can produce these gases, so it's crucial to have a thorough understanding of the planet's environment and geology before drawing any conclusions about the presence of life. The discovery of potential biosignatures on Mars has given a huge boost to the field of astrobiology. It has shown that the search for life beyond Earth is not just a pipe dream, but a real possibility. It has also highlighted the importance of studying Mars in more detail and of sending future missions to collect more samples and search for further evidence of life. The Perseverance rover is just the first step in this exciting journey. Future missions could involve drilling deeper into the Martian surface, searching for evidence of past or present life in the subsurface environment. It's also possible that we could one day send a robotic mission to return Martian samples to Earth, where they can be analysed in state-of-the-art laboratories with the most advanced scientific instruments. But the search for life beyond Earth is not just about finding other organisms, it's also about understanding the origin and evolution of life itself. By studying life on other planets, we can learn more about the conditions that are necessary for life to arise and about the processes that drive its evolution. This knowledge could help us to better understand the origins of life on Earth and to predict the future of life on our own planet. Think about the implications of finding life on another planet. It would be one of the most profound discoveries in human history. It would change our understanding of our place in the universe, and it would raise fundamental questions about the nature of life itself. It would also have profound implications for our future, inspiring us to explore the cosmos and to seek out new worlds. Imagine a future where humans have established colonies on other planets, where we are living alongside other forms of life. It would be a future of incredible diversity and opportunity, a future where the possibilities are limitless. But the search for life beyond Earth is not just about science. It's also about philosophy and spirituality. It's about asking the big questions about our existence and about our relationship to the universe. Are we alone? What is the meaning of life? These are questions that have been asked for centuries, and the search for life beyond Earth may finally provide us with some answers. The discovery on Mars, however subtle, has reignited these questions with a new urgency. The potential presence of past life on our planetary neighbour has brought the search for extraterrestrial life into sharp focus. It forces us to consider the implications of such a discovery, not just for science, but for humanity as a whole. It's a humbling experience to realise that we may not be alone in the universe. It challenges our anthropocentric view of the world, and it forces us to consider the possibility that life may be more common than we previously thought. It expands our horizons and inspires us to think beyond the confines of our own planet. The search for life beyond Earth is a testament to human curiosity and our relentless pursuit of knowledge. It's a journey that will take us to the far reaches of the solar system and beyond, and it may ultimately lead us to the discovery of life on other worlds. But we must also proceed with caution and with a healthy dose of skepticism. The search for life beyond Earth is a complex and challenging endeavour, and it's important to avoid jumping to conclusions. We need to be rigorous in our analysis and to rule out all other possible explanations before claiming that we have found evidence of life. The scientific process is one of constant questioning and refinement. We must be willing to challenge our own assumptions and to consider alternative explanations. This is especially important when dealing with such a profound and potentially controversial topic as the search for life beyond Earth. And what if, after all this searching, we find nothing? What if Earth truly is unique in the universe? Even then, the search will not have been in vain. The knowledge and technologies that we develop in the course of our search will have countless other applications, benefiting humanity in ways that we cannot even imagine. The search for life beyond Earth is a journey of discovery, and the destination is not as important as the journey itself. It's a journey that will challenge us, inspire us, and ultimately help us to better understand our place in the universe. But as we continue this search, and as we analyse the data coming back from Mars, we must remember the importance of critical thinking and scientific rigour. We must be open to the possibility of life beyond Earth. But we must also be cautious about drawing premature conclusions. We must let the evidence guide us, and we must be willing to accept whatever the evidence may reveal. The potential discovery of life on Mars is an incredible opportunity, but it's also a responsibility. It's a responsibility to approach the search with integrity and with a commitment to the scientific method. It's a responsibility to share our findings with the world and to engage in open and honest discussions about the implications of our discoveries. So, let us continue to explore, to question, and to seek out new knowledge. Let us continue to push the boundaries of science and to unravel the mysteries of the universe. Let us continue to search for life beyond Earth, with the hope that one day we will finally answer the age-old question, are we alone? But this discovery was only the beginning, because next we uncover the crucial element of scientific skepticism and the alternative explanations that could challenge everything we thought we knew about life on Mars. Chapter 7. Caution and Controversy. The scientific process. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust-coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to life? Now, we've journeyed together to Jezero Crater, explored its ancient riverbeds and lake sediments, and discovered compelling evidence of minerals like vivianite and greigite, minerals that, on Earth, are often associated with microbial life. The implications are staggering, aren't they? We stand on the precipice of potentially rewriting textbooks, of answering one of humanity's most profound questions: are we alone? But before we declare victory, before we etch life on Mars into the annals of science, we must pause. We must proceed with caution. Science, after all, is not about leaping to conclusions, no matter how tantalizing they may be. It's about rigorous testing, relentless questioning, and an unwavering commitment to objectivity. Think of it like building a bridge. You can't just slap some planks together and hope for the best. You need blueprints, careful calculations, and the strongest materials. You need to test every joint, every cable, every support. Because if you don't, that bridge could collapse. And in science, a collapse theory can set us back years, even decades. So, what does this caution look like in the context of our Martian discovery? It means acknowledging that while vivianite and greigite are often linked to life on Earth, they can also form through purely geological processes. It means considering alternative explanations for their presence in Jezero Crater, explanations that don't involve Martian microbes. Perhaps these minerals were formed by volcanic activity, or by the interaction of water with specific types of rocks. Maybe they were created by unusual chemical reactions that we don't fully understand. The possibilities are numerous, and we must explore each one with meticulous care. This is where the scientific process truly shines. It's a system designed to weed out biases, to challenge assumptions, and to ensure that only the most robust and well-supported ideas survive. It's a process that relies on skepticism, on peer review, and on the collective wisdom of the scientific community. Let's delve into the world of peer review. Imagine you're a scientist who's just made a groundbreaking discovery. You've analysed your data, written up your findings, and submitted your research paper to a prestigious journal. What happens next? Your paper doesn't simply get published. It's sent to other experts in your field, scientists who are intimately familiar with the subject matter. These experts, your peers, will scrutinize your work with a critical eye. They'll examine your methods, question your interpretations, and look for any potential flaws in your reasoning. They might even try to replicate your results to see if they hold up under scrutiny. This process can be brutal. Your work might be torn apart, your assumptions challenged, and your conclusions questioned. But it's also essential. It's how science ensures that its findings are reliable and trustworthy. It's how we separate genuine breakthroughs from wishful thinking. And even after a paper is published, the scrutiny doesn't end. Other scientists will read it, analyze it, and try to build upon it. They might find new evidence that supports your conclusions, or they might uncover new data that contradicts them. This constant cycle of questioning and testing is what drives scientific progress. Think of the early days of plate tectonics. Alfred Wegener, a German meteorologist, proposed the theory of continental drift in the early 20th century, suggesting that the continents were once joined together in a supercontinent called Pangaea. He pointed to the matching shapes of the coastlines of Africa and South America, as well as the similarities in their fossil records. but his ideas were met with fierce resistance. Many scientists dismissed his theory as pseudoscience, arguing that there was no known mechanism that could explain how continents could move across the Earth's surface. Wegener struggled for years to gain acceptance for his ideas, but he died in 1930 without seeing his theory widely embraced. It wasn't until the 1960s, with the discovery of seafloor spreading and plate tectonics, that Wegener's ideas were finally vindicated. Scientists realized that the Earth's surface is made up of a series of plates that are constantly moving and interacting with each other. This discovery revolutionized our understanding of geology and transformed our view of the planet. The lesson here is clear. Even the most groundbreaking ideas must be subjected to rigorous scrutiny before they can be accepted as scientific fact. And even then, our understanding is always provisional, always subject to revision in the light of new evidence. So, what are some of the alternative explanations for the presence of vivianite and greigite in Jezero Crater? Let's start with the possibility of abiotic formation. As we discussed earlier, these minerals can form through purely geological processes, without the involvement of living organisms. For example, vivianite can form when iron-rich groundwater comes into contact with phosphate-rich sediments. This can happen in a variety of environments, including volcanic terrains and hydrothermal systems. Similarly, greigite can form through the chemical alteration of iron sulfides, which are common in many types of rocks. It's also possible that these minerals were formed by processes that are unique to Mars, processes that we don't fully understand. Mars is a very different planet from Earth, with a different atmosphere, a different geology, and a different history. It's possible that these differences could lead to the formation of minerals through pathways that are not common on Earth. Another possibility is that the minerals were formed by non-biological organic matter. Organic molecules, which are the building blocks of life, can also be produced through abiotic processes. For example, they can be synthesized in hydrothermal vents or in the atmosphere through the action of ultraviolet radiation. If these organic molecules were present in Jezero Crater, they could have interacted with iron and phosphate to form vivianite and greigite. This scenario wouldn't necessarily imply the existence of life on Mars, but it would still be a significant discovery, as it would suggest that the planet was once capable of producing the raw materials for life. And what about contamination? Could it be possible that the minerals were somehow introduced to Jezero Crater by the Perseverance rover itself? This is a serious concern, as the rover is not completely sterile. It carries with it a small number of terrestrial microbes which could potentially contaminate the Martian environment. To mitigate this risk, NASA has taken extensive precautions to sterilize the rover and its instruments. But it's impossible to eliminate the risk completely. It's possible that some microbes could have survived the sterilization process and hitched a ride to Mars. If these microbes were able to thrive in the Martian environment, they could potentially alter the chemistry of the rocks and soils, leading to the formation of minerals that would not otherwise be present. This is why it's so important to carefully analyze the samples collected by Perseverance and to compare them to samples collected from other locations on Mars. So, how do we address these alternative explanations? How do we determine whether the vivianite and greigite in Jezero Crater are truly biosignatures, or whether they were formed through purely geological processes? The answer lies in a combination of careful analysis, rigorous testing, and continued exploration. First, we need to analyze the samples collected by Perseverance in as much detail as possible. We need to determine their chemical composition, their crystal structure, and their isotopic ratios. We need to look for any evidence of organic molecules such as lipids, proteins, or DNA. We also need to compare the Martian samples to samples collected from similar environments on Earth. We need to study the formation of vivianite and greigite in terrestrial environments and to identify the key factors that influence their formation. And finally, we need to continue exploring Mars. We need to send more rovers, landers, and orbiters to the planet to gather more data and to search for other potential biosignatures. We need to drill deeper into the Martian subsurface, where liquid water may still exist, and to look for evidence of past or present life. The search for life on Mars is a marathon, not a sprint. It's a long and arduous process that will require patience, perseverance, and a healthy dose of skepticism. But the potential reward is enormous. If we can find evidence of life on Mars, it would revolutionize our understanding of the universe and our place within it. It would tell us that life is not unique to Earth. that it can arise in other environments, and that it may be far more common in the universe than we previously thought. It would also have profound implications for our future, as it would open up the possibility of colonizing other planets and of expanding our civilization beyond Earth. But let's be clear, even if we don't find evidence of life on Mars, the search will still be worthwhile. The process of exploring Mars, of studying its geology, its atmosphere, and its climate will teach us a great deal about our own planet. It will help us to understand the processes that shape Earth and to predict how our planet might change in the future. It will also inspire us to push the boundaries of science and technology, to develop new tools and techniques for exploring the universe. And it will remind us of the importance of curiosity, of exploration, and of the human spirit. So, as we continue to analyze the samples collected by Perseverance, let's remember the importance of caution and skepticism. Let's not jump to conclusions, no matter how tempting they may be. Let's embrace the scientific process with all its rigor and its challenges. Let's be patient, let's be persistent, and let's be open to the possibility that the truth may be more complex and more nuanced than we initially imagined. Because in the end, the pursuit of knowledge is its own reward. And as we move forward, remember this: the discovery of potential biosignatures on Mars is not the end of the story, it's just the beginning. It's a starting point for a new era of exploration and discovery, an era that will challenge our assumptions, expand our horizons, and ultimately transform our understanding of the universe and our place within it. But this discovery was only the beginning, because next we uncover what this means for humanity's future. Chapter 8: Implications for Humanity's Future. Imagine for a moment that you are standing on the surface of another world. The sky above you is not the familiar blue of Earth, but a dusty orange that stretches endlessly across an alien horizon. The ground beneath your feet is covered in rust-coloured soil that has remained undisturbed for billions of years. This is Mars, our planetary neighbour, a world that has captivated human imagination for centuries. But what if I told you that this seemingly barren landscape might once have been home to life? The discovery of vivianite and greigite in Jezero Crater, minerals often associated with microbial activity on Earth, has sent shockwaves through the scientific community. The implications are staggering. Could this be evidence that life once existed, or perhaps even still exists, on Mars? What would such a discovery mean for our understanding of life in the universe and for our own place within it? The immediate impact would be a surge in Mars exploration. Funding for future missions would likely increase dramatically as scientists clamour to further investigate Jezero Crater and other promising locations on the Red Planet. More sophisticated rovers, equipped with advanced analytical instruments, will be deployed to search for additional biosignatures and, ultimately, definitive proof of past or present life. But it wouldn't stop there. The discovery of life on Mars would revolutionise astrobiology, the study of the origin, evolution, distribution, and future of life in the universe. It would provide a tangible example of life existing beyond Earth, allowing scientists to refine their theories about the conditions necessary for life to arise and the types of biosignatures to look for on other planets and moons. The search for life beyond Earth would no longer be a purely theoretical exercise. It would be grounded in the reality of life having once thrived, or perhaps still thriving, on our nearest planetary neighbour. Consider the implications for our understanding of the origins of life itself. If life arose independently on both Earth and Mars, it would suggest that the process is relatively common in the universe. This would dramatically increase the likelihood of finding life on other planets and moons, perhaps even within our own solar system. It could also provide valuable insights into the different pathways that life can take, helping us to understand the diversity of life that might exist elsewhere in the cosmos. But what if the discovery on Mars is not just evidence of past life, but of present-day organisms? The possibility, however remote, that microbial life still exists beneath the Martian surface cannot be ruled out. If this were the case, it would open up entirely new avenues of research. Scientists would be eager to study these Martian microbes, to understand their unique adaptations to the harsh Martian environment, and to compare them to life on Earth. Could Martian life share a common ancestor with terrestrial life? Or would it represent a completely independent origin of life, a second Genesis? The ethical considerations surrounding the potential discovery of extant life on Mars would be profound. How would we protect Martian life from contamination by Earth-based organisms? Would we have the right to exploit Martian resources, even if it meant potentially harming or destroying Martian life? These are complex questions that would require careful consideration and international cooperation. The discovery of life on Mars would also have a profound impact on our perspective on Earth. It would force us to confront our place in the universe and to consider the possibility that we are not alone. It could lead to a greater appreciation for the fragility and uniqueness of life on Earth, and to a renewed commitment to protecting our planet from environmental degradation. After all, if life can arise and thrive on other worlds, it underscores the preciousness of the life we know here at home. Imagine the inspiration it would give to future generations. The discovery of life on Mars would ignite the imaginations of young people around the world, inspiring them to pursue careers in science, technology, engineering, and mathematics. It would fuel a new era of space exploration, as humanity sets its sights on even more ambitious goals, such as establishing a permanent human presence on Mars and searching for life on other planets and moons throughout the solar system and beyond. Think about the technological advancements that would be spurred by the search for life on Mars. The development of new rovers, landers, and orbital spacecraft, equipped with increasingly sophisticated instruments, would drive innovation in a wide range of fields, from robotics and artificial intelligence to materials, science, and biotechnology. These advancements would not only benefit space exploration, but also have applications in other areas such as medicine, energy, and environmental science. The potential economic benefits of Mars exploration and the search for life beyond Earth should not be overlooked. The development of new technologies and industries related to space exploration could create jobs and stimulate economic growth. The discovery of valuable resources on Mars, such as water ice, could also have significant economic implications, potentially paving the way for a self-sustaining human presence on the red planet. But let's not get ahead of ourselves. It's crucial to remember that the discovery of vivianite and greigite in Jezero Crater is not definitive proof of life on Mars. These minerals can also form through non-biological processes. More research is needed to determine the origin of these minerals and to search for other, more conclusive biosignatures. The scientific process demands skepticism and rigorous testing of hypotheses. Scientists must be cautious about making premature claims of life on other worlds. The history of science is filled with examples of false alarms and misinterpretations. It is essential to gather as much evidence as possible and to carefully consider all alternative explanations before drawing any firm conclusions. The peer review process plays a crucial role in ensuring the integrity of scientific research. Before any findings are published in a scientific journal, they must be reviewed by other experts in the field. This helps to identify potential errors, biases, and alternative interpretations. The peer review process is designed to ensure that only the most rigorous and well-supported findings are disseminated to the wider scientific community and the public. Despite the need for caution, the discovery of vivianite and greigite in Jezero Crater is a significant step forward in the search for life beyond Earth. It provides a compelling reason to continue exploring Mars and to search for other potentially habitable environments throughout the solar system. It reminds us that the possibility of life existing beyond Earth is not just a science fiction fantasy, but a real and scientifically plausible possibility. The implications of potentially finding life on Mars are profound. It would revolutionize our understanding of life in the universe, inspire future generations, and drive technological innovation. It would also force us to confront our place in the cosmos and to consider the ethical implications of exploring and potentially colonizing other worlds. The search for life on Mars is a testament to human curiosity and our relentless pursuit of knowledge. It is a journey that will undoubtedly lead to new discoveries and insights, regardless of whether or not we ultimately find evidence of life. The very act of exploring the universe and searching for life beyond Earth is a transformative experience that can broaden our horizons and deepen our understanding of ourselves and our place in the cosmos. Think about the impact on future exploration missions. The discovery of potential biosignatures in Jezero Crater would undoubtedly influence the design and objectives of future Mars missions. Scientists would be eager to send more advanced rovers and landers to Jezero Crater to further investigate the site and to search for more conclusive evidence of life. They might also consider sending a sample return mission to bring Martian rocks and soil back to Earth for detailed analysis in terrestrial laboratories. The search for life on Mars could also lead to the exploration of other potentially habitable environments in the solar system, such as Europa, Enceladus, and Titan. These moons are thought to harbour subsurface oceans that could potentially support life. Future missions could be designed to probe these oceans and to search for biosignatures in the water. The discovery of life on Mars would also have a profound impact on our understanding of the potential for life to exist beyond our solar system. It would provide a valuable data point for astrobiologists who are trying to estimate the number of habitable planets in the Milky Way galaxy and the likelihood of life arising on those planets. It could also inspire the development of new technologies for detecting biosignatures on exoplanets, planets orbiting other stars. Imagine the day when we finally receive definitive proof of life on another world. It would be a moment of profound significance for humanity, a moment that would change our understanding of the universe and our place within it. It would be a moment that would inspire awe and wonder, and that would remind us of the incredible potential for life to exist throughout the cosmos. But what if we never find life on Mars? Would that mean that we are alone in the universe? Not necessarily. The absence of life on Mars would not rule out the possibility of life existing elsewhere. There are countless other planets and moons in the universe, and it is entirely possible that life has arisen on some of them. The search for life beyond Earth is a long and challenging one, but it is a search that is well worth pursuing. The journey to understand our place in the universe is a continuous one. Each new discovery, each new insight brings us closer to a deeper understanding of ourselves and the cosmos. The search for life beyond Earth is an integral part of this journey, a journey that will undoubtedly continue to captivate and inspire us for generations to come. Consider the potential for future colonization. While the discovery of life on Mars would raise ethical questions about the potential impact of human activity on Martian ecosystems, it could also pave the way for future human colonization of the red planet. If Mars were found to be habitable, even if only by microbial life, it could become a target for human settlement, as humans seek to expand beyond Earth and to establish a permanent presence on another world. The challenges of colonizing Mars would be immense, but the potential rewards could be even greater. A self-sustaining human colony on Mars could serve as a backup for humanity in the event of a catastrophic event on Earth. It could also provide a base for further exploration of the solar system and for the development of new technologies and resources. The ethical considerations surrounding the potential colonization of Mars would need to be carefully considered. How would we ensure that human activities do not harm or destroy Martian life? How would we protect the Martian environment from contamination? How would we govern a Martian colony and ensure that it is a just and equitable society? These are complex questions that would require careful consideration and international cooperation. The discovery of life on Mars, whether past or present, would undoubtedly spark a renewed debate about the future of humanity in space. It would force us to confront our responsibilities as stewards of the universe and to consider the long-term implications of our actions. It would be a moment of profound reflection, a moment that could shape the course of human history for centuries to come. But for now, let's return to the present. The discovery of vivianite and greigite in Jezero Crater is a tantalizing clue, a hint that Mars may once have been a very different place, a place where life could have thrived. It is a reminder that the search for life beyond Earth is not just a scientific endeavor, but a deeply human quest to understand our place in the universe and to answer the age-old question, are we alone? The universe is vast and mysterious, and there is still so much that we do not know. But with each new discovery, with each new insight, we move closer to a deeper understanding of the cosmos and our place within it. The search for life beyond Earth is a journey of discovery, a journey that will undoubtedly continue to captivate and inspire us for generations to come. The implications for humanity's future are enormous, stretching from the depths of scientific understanding to the heights of philosophical inquiry. The potential discovery of life on Mars is not just about finding little green men or microscopic organisms. It's about redefining our understanding of life itself, our place in the cosmos, and our responsibilities to the universe around us. It's a moment of both immense excitement and profound humility, a reminder that the universe is full of surprises and that there is still so much left to discover. It's a journey that will challenge us, inspire us, and ultimately change us. It's a journey that is just beginning. But this discovery was only the beginning, because next we uncover a hidden network of tunnels beneath the Martian surface. Tunnels that may hold the key to understanding how life could have survived on Mars for billions of years.